Hi, and welcome to 9.1, new chapter, and this is 9.1 Exploring Rational Functions Using Transformations Part 1. So this will be the beginning of 9.1. I think we're going to have 3 different videos for 9.1, so this will be the first one. So first of all, what is a rational function? A rational function, similar to a rational number, which can be expressed as a fraction, a rational function is a function that can be expressed as a fraction where the top and the bottom, the numerator and the denominator, are both polynomials. So one of the easiest, the most straightforward examples here is if we said, say, perhaps 1 over x. But we're going to see a whole variety of types of polynomial numerators and denominators as we work through this function. So our first task here is let's sketch the graph of f of x is equal to 1 over x. So let's pick some values here for x and let's think about what we get for y, what we get for f of x. So I'm going to put a 0 in the middle here. And the first thing we realize that if I put in a 0, that I'm breaking the rules of math, right? I'm trying to divide by 0. So 1 divided by 0 is undefined. So I'm going to write here undefined. And if I go up to 1 here, 1 divided by 1 is 1. And if I put in a 2 here, 1 divided by 2 is a half. And let's just put in a really big number here. Let's say 100. So that number over here would be 1 over 100. So if I start to graph that, first of all, I can't put anything in 0. But if I put a 1 in for x, I get a 1 for y. If I put in a 2 for x, I get a half. Of course, I can't put a 100. I could put a 3, then I would get a third. But you can see the effect here. As my x gets larger and larger, I'm getting closer and closer to the axis. I'm getting closer and closer to the x-axis. There's no possible, regardless of how large I make that denominator, I can never make it hit 0. So 1 divided by a very large number approaches but never hits 0. So we're going to see that kind of asymptotic behavior along this unit very, very often. Now let's try in the other direction. So if I've got 0 is undefined, if I go negative 1, so 1 divided by negative 1 is negative 1. Negative 2, I get negative 1 half. So let's, let's take over here. So negative 1 is negative 1. Negative 2 is negative 1 half, and negative 3 would be negative 1/3. And again, we see this kind of behavior as I make x approach negative infinity. As x gets exceedingly large in the negative direction, y gets very close to but never touches that x-axis, never hits 0. So what about between 0 and 1? I guess I left a little bit of space here. So if I made x equal to a half, what would y be? 1 over 1 half. So it's the same thing as 1 multiplied by the reciprocal, so that's the same thing as 2. So quickly you could just say 1 half, the reciprocal of that is 2. If I did negative 1 half, the reciprocal of that would be negative 2. So here I'll put negative 1 half for x, I get a 2 here. And you can see also if I got very, very close to 0 for my x, if I put a very small number in for x, let me just erase some of this. If I put in, let's say, 1 over 0.0001, that's a thousandth. 1 divided by a thousandth is equal to 1,000. So in other words, if I put in for x a very small number, very, very close to 0, my y comes out very, very large. So I get this shape here. And we may have seen this shape in the past, right? And we have two asymptotes. Instead of trying to do the dash sign, I'm going to use a kind of a dash highlighter here. So there is my horizontal asymptote, and there is my vertical asymptote. I have 2 of them here. So let's see if we can describe this down below. It says, note x is equal to 0 is equal to a non-permissible value. This creates a vertical asymptote. So I'm going to write VA for the vertical asymptote. So this piece right here, there is my vertical asymptote. And that vertical asymptote, you can define that. That line would be at x equals 0. And here is one way to describe it. When x approaches infinity. So as x gets very large, so we're talking about this area right here, as x gets very large, y approaches 0. And when x approaches negative infinity, so now this is this section here, then y approaches 0. So this behavior here, this piece right here, that's what's creating my horizontal asymptote. So that's my horizontal asymptote. Oh, did I write this improperly? The vertical asymptote, sorry, here I'm just going to switch one thing. This one here is my horizontal asymptote. That was what I'm talking about, the horizontal asymptote. And that is the x-axis at y is equal to 0. And this is my vertical asymptote at x equals 0. Okay. The curves are in quadrant 1 and quadrant number 3. Now, we're going to make a slight little shift here. And we're going to graph f of x is equal to negative 1 over x. So what happens is all these x values stay the same, but my y values are opposite. So here I'm going to pause and make my graph quickly. Okay, so here is my graph of negative 1 over x, and you can see how it's changed. From here we're in quadrant 1 and quadrant 3, and now we're in quadrant 2 and quadrant 4. There's still a vertical asymptote at x equals 0, and so the x equals 0, I'll do this dashed line in white and yellow, and we have a horizontal asymptote at y is equal, I always get the x and the y, at y is equal to 0. So I hope that makes sense for you, because all we did was keep the x values the same and multiply the y values by negative 1. Let's take a look at the next page. Note that if you have the negative 1 over x, it's the same thing as negative 1 over x. As long as you just have one negative sign altogether, the values are the same. Well, let's take a look at this next one. It says, given f of x is equal to 1 over x, sketch the graph of y is equal to 3 times the f of x plus 2 minus 1. Now, we're going to use the language of transformations here, so you can see what's happened, that we have taken we've shifted things 2 to the left. Here, we'll take a look at this. This part here means that we are going 2 to the left. And what did that do? Now my vertical asymptote has shifted over 2 to the left, right? Maybe I'll highlight that like this. Oops, try better. It's gone 2 to the left. Now my other color highlighter, this part has shifted it 3 down. Or sorry, 1 down. And you can see that result because you can see this asymptote has shifted down. Now it's down at negative 1 instead of right along the axis. Now the last bit, the 3, which is our other change, it's a little bit harder to see, but the way that the 3 works is that it stretches these lines here. And I'm going to get Desmos out and we'll see if we can make that work. Okay, so here I am at Desmos. I'm just going to put in our original graph here. We got y is equal to 1 over x, and you can see that nice graph that it makes for us. You can see that when you're graphing this, the x multiplied times the y is always going to be equal to 1. So here my x value is 1 and my y value is 1. If I slide this over by 2, now my x is 2 and my y is a half. So if I multiply those together, I also get 1. And this is often a little shorthand for when you're graphing. So here I get 4 and a quarter, and again, those multiplied together are equal to 1. So it's a quick way to try to figure out where to put your dots is you think, okay, the x times the y has to be equal to that 1 there. Let's make another graph. I'm going to say y is equal to a over x, and say yes, let's make a slider. And so as I slide this over, look what happens to the graph. It stretches vertically, but you'll see that really kind of just moves away from the origin a little bit. So I'm going to leave that at 4 for a second, and let's explore a few points. Here it is at 2 and 2 again, because remember that principle we had a second ago. The two dots, in this case now, they're going to be multiplying out to the 4. So 2 times 2, and here we have a 4 times a 1. If I go all the way up to 8, if I can find the right spot, it would be 8 times a half. Very, very close to it there if I can find it there, and 8 times a half. So those two numbers always multiply out to 4. And you can see what that stretch does right over there, okay, when we add it together. Now if I go and I put on the bottom here, and if I say x minus h, and I say, yeah, I need another slider for that, look what the h does here. I'll get rid of the old one. And I'll put this back at 1 just to kind of make it normal again. Okay, so what does the h do? It slides it left and right. And although Desmos doesn't put in the asymptote, the vertical asymptote, you can see it slide around. So as I change this h value, just like in our transformations before, you can see it slide around. And the very last one I'm going to do is put in that plus k here. So when I do the k, I'm going to say, yeah, give me a slider for k. I can slide that up and down, and you can see that that horizontal asymptote and everything else will be moving with it. So that's really what we're learning today in a nutshell. Is this is the graph-friendly way that for us to show a function, where a is going to be this amplitude here, and I'll show you the way that amplitude works. Okay, and our h and our k slide it around. And hey, just for fun, let's see what happens if we make a negative value. So if we make an a is a negative value, well, we saw that earlier, right? It changes which quadrants it's in. Instead of quadrant number 1 and quadrant number 3, it's in 2 and in 4. So back at our notes here, this would be the graphing friendly way I was talking about to draw this function. So here is my a value of 3, and there's my h value of minus 2, which moved it left 2, and here is my negative 1, which caused it to go down 1, to move down 1. I hope you can see those connections. So there is our general equation of the rational function, and you'll notice that x equals a, h will be our vertical asymptote, and y is equal to k is our horizontal asymptote. And just like we did before, you remember that the h is going to be in the form of x minus h. So in our example that we just had, when we have x plus 2, our h is equal to negative 2. I can't write very well here. H would be equal to negative 2 in this case. All right, so using the above graph, explain the behavior for the values of the variable around the non-permissible value. Also explain the end behavior of the graph. Alright, so we really have two things to do. The first one is, I'll just put a 1 by there, is explain the behavior of the graph for values of the variable around the non-permissible value. So this non-permissible value, I'm often going to use the letters just NPV for that. So let's go back. What is the non-permissible value? Well, if you look at, you can see it from the function here, the non-permissible value is when we would be dividing by 0. So the non-permissible value comes from the fact that the denominator x plus 2 cannot be equal to 0. So therefore x cannot be equal to negative 2. And if you're looking at our graph, this is the value of x that creates this vertical asymptote. So the question is, explain the behavior of the graph for values of the variable around it. Well, as x approaches that value, as it approaches from the left, y gets exceedingly large. As it approaches from the right, y gets exceedingly large, but in the negative version. So what I'm going to do, the way I'm going to explain that, I'll say here, this is my explanation number 1. I'm going to say as x, and now my arrow means approaches, so as x gets closer and closer to negative 2, what happens is that y gets closer and closer, approaches. Now, depending on which side it's approaching from, it's either going to be approaching positive infinity, that's all the way up, or negative infinity. So that's describing this asymptotic behavior of the graph of here as it's going up this way, as x is approaching from the right hand side, y is approaching positive infinity, and over here as x approaches from the left hand side, as it gets closer and closer to that -2, the y value will be approaching negative infinity. Okay, so that's the first thing we did. The second thing that we need to do here, also explain the end behavior of the graph. So this is point number 2. So the end behavior of the graph, that means these ends over here. So this end and this end over here. So again, we have as x gets exceedingly large, as x approaches positive infinity, the y value in this case approaches -1. So I'm going to write down here, I'm going to say as x approaches positive infinity, y gets closer and closer, but never actually touches -1. And from the other side, looking on the left, as x approaches negative infinity, as it gets becomes an exceedingly large negative number, then y is getting closer and closer to -1 as well. So all I'm going to do is say as x approaches both positive or negative infinity. So this is kind of my shorthand here for explaining the behavior of the graphs around the non-permissible value and the behavior of the graph. So what this part does, was part number 1 does here, this creates a vertical asymptote at x equals -2. And what this part does is create a horizontal asymptote at y is equal to -1. Alright, so let's take a look at this next one. Here we're going to sketch the graph of 1 over x minus 3 plus 1. So first of all, where will our non-permissible value be? The non-permissible value is from that x minus 3, and we could say x minus 3 cannot be equal to 0. In other words, x cannot be equal to 3. So we'll put this one here. That will be our non-permissible value. What is our x-intercept? So on a graph, the x-intercept, if just looking over here, is where something crosses the x-axis. So we want to find out what the x value is when the y value is equal to 0. So here I'm going to put sort of like, what's the x value when y is equal to 0? So the way to do this, here I'll get a little workspace, is to actually put in a 0 value for y. So if I say 0 is equal to 1 over x minus 3 plus 1, and now we want to solve for this, well, I guess we'll subtract 1 from each side, so we'll get -1 is equal to 1 over x minus 3. Now if I multiply both sides by x minus 3, I'll get negative x minus 3 is equal to 1. I get x minus 3 is equal to -1. Now if I add both sides, 3 to both sides, I'll get x is equal to 2. So what happens? Where will it cross the x-axis? What is the x-intercept? X equals 2. In other words, it'll cross at 2, 0. So we have one of our points. What is the y-intercept? So the y-intercept is when x is 0, what's the y value? So for this one, we plug in a 0 for x, so it's a little bit easier to look at. Maybe if I do my work in blue here, I can say if I have y is equal to 1 over, now instead of writing x minus 3, I'm just going to write minus 3 because x is equal to 0 plus 1. -1/3 plus, now 1 is the same thing as 3/3, so I'm going to get 2/3. So my value here will be 0, 2/3. My vertical asymptote. Now the vertical asymptote is the result of this x non-permissible value. You know what? I should probably write the non-permissible value, say that x cannot be equal to 3. So rather than thinking there's a spot there. So at x cannot be equal to 3, it will say we have a vertical asymptote at x equals 3. You know what, let's write that in right away. So we've got an x equals 3. Here, I'll erase my little mark here. So we've got a vertical asymptote. I'll start a tradition here. I'm going to be doing my asymptotes in dashed highlighter. There we go. Now what about the horizontal asymptote? So you remember how this works. the horizontal asymptote is going to be from this value over here, from that plus 1. Everything's going to be raised 1. So my horizontal asymptote will be horizontal asymptote at y is equal to 1. So moving over here, I get a y is equal to 1 horizontal asymptote. Now we've got a pretty good sense of how it's going to look because we know the general shape of these things. Since it's going to be positive, we're going to be getting some shape here. And it's not exactly quadrant 1 and quadrant 3, but if this is similar to what my x and my y axes are, it's going to be right in this space here and in that space there. That's where I'm going to be drawing my graph. So it's kind of like a version of quadrant 1 and quadrant 3. So what will the domain be? Well, I'm not sure if I have enough space here, but I'm going to write those kind of cool curly braces here. And I'm going to say x such that. Now what can x not be? It can be anything. We can plug anything in there except we can't put a 3 in there, because when we put a 3 in, then we're doing our division by 0 error. So x can be anything but 3, so I'm going to say x cannot be equal to 3, and x is an element of this set of real numbers, end curly brace. How about range? Range is very similar in that it can be anything, but y cannot be equal to 1, because regardless of how large or how small I make x, I can never get y to be 1. So I'm going to put a curly brace y such that y cannot be equal to 1, and y is a member of an element of the real numbers. So it can be anything, but it can't be equal to 1. Alright, so we're almost ready to do our graphing. You remember that this value is 1, so kind of a quick way to think about our graphing. Can sort of think of this as your origin, and we want to go to the right and up some numbers that multiply out to 1. So if I go right 1, up 1, that's going to be a good spot. I could go right 2, so I'm going to go right 2, up a half, right? Because I'm thinking about what are some numbers that are equal to 1. So here I'm going right 2, up a half, okay? And here I could go right a half, up 2. All right, so I could go here, I'll erase this business here. I could go right a half, up 2, and then over here. And I could go right a third, up 3, and go to here. So now I'll try to sketch this line in. Okay, and you know what? Let me take one of these ones. Let's take this one here, and this is at 4, 2. And let's just check to see whether or not it works. So if I start off with y is equal to 1 over x minus 3 plus 1, and now my x is 4 and my y is 2. Let's try it out. So I'll say 2 is my y is equal to 1 over 4 minus 3 plus 1. 4 minus 3 is 1. 1 over 1 is 1, so I can say 2 is equal to 1 plus 1. Yeah, it seems to work out. So I've verified that 4.2 is indeed one of the values. Now, my other place, thinking again from moving from here, I want to move all the different combinations of left and down in this case, or down and left, that multiply out to 1. So the obvious choice is to go over here first and go 2 over and half down. I can go 3 over and a third down, 2 down and half left, 3 down and a third, and so on. And so now I'll get this kind of a shape here. I'll see if I can sketch it in. There we go. And here, this is a point here. This would be an x value of 2 and a y value of 0. Which reminds me, we do have calculated here. We've got an x-intercept of 2, 0. That's the one I just put in. And we have a y-intercept of 0, 2/3. So that looks pretty good. 0, 2/3. That would be this one right here. So we get 0, 2/3 over there. All right, so there is our graph. I hope you're starting to get the hang of it. We've got a few more examples that I will do for you, and you can kind of play along at home, I guess. All right, so this one, a few things that we're going to realize right away. This is a negative version, right? So instead of having, quad here and here, in this case, it'll be something more like there and there. But of course, my asymptotes are going to be shifted over because of this -1 and the 3 as well. So let's try it out. We've got here, what is my non-permissible value? So looking at the denominator, x minus 1 cannot be equal to 0, so I'm going to say x cannot be equal to 1. What is my x-intercept? Well, that takes a little bit of effort here. I'm going to say, my x-intercept, that means what's my x value when y is equal to 0? So my y value is 0, so I'm going to write 0 is equal to -2 all over x minus 1 plus 3. I'm going to subtract 3 from both sides, so I'll get -3 is equal to -2 over x minus 1. Now here's something, if I kind of look at this and think of it as two fractions, kind of a shortcut sometimes is I can say these two here, I can switch places. So really mathematically what I'm doing is multiplying both sides by x minus 1 and dividing both sides by -3. So what does that leave me with? It ends with x minus 1 is equal to -2 over -3. See how I've switched those two? And I've dropped the over 1. So -2 over -3 is the same thing as 2 over 3. So now my x is going to be equal to 1 plus 2/3. Or we can say 3/3 plus 2/3, 5/3, however we want to look at it. So there's my value for my x-intercept. My x is going to be equal to 5/3, 0. In fact, I'll just go over here right away. So here's 3, 4, 5, 1 and 2/3 right about there. There's my spot, and I guess I can even label that. That is a 5/3 right there. My y-intercept. So I'll say my y-intercept. What is y-intercept? It is when my x is 0, what's my y value? So my y is going to be equal to -2 divided by, now again I'll just replace that x with a 0, so I'll say over -1 plus 3. -2 over -1 is the same thing as +2 over 1, so that's 2 plus 3, so y is equal to 5. So my value for my y-intercept will be my x is 0 and my y is 5. So my spot would be right over here, and I get a 0, 5. I'll just label that, and that I'm going to anticipate that that will be a point. My vertical asymptote, so my vertical asymptote comes from my non-permissible value here. So my vertical asymptote is going to be at x equals 1. So I'll just write that one in right away at x equals 1. Here comes the vertical asymptote. And my horizontal asymptote is going to be from the shifting over 1 to the, my horizontal asymptote is from shifting up 3, pardon me. So up 3, so here I'm going to say my horizontal asymptote is, when we go up 3, I'm going to say y is equal to 3. So now I say here, my y is equal to 3. There is my other asymptote. And thinking that, again, the fact that it's negative kind of corresponds with the fact that it's going to be down to the right and up to the left. Now the last, I guess I should type the domain here. The domain is x cannot be equal to 1. Here, I'll just pause and do these quick. So for my x, my domain, x cannot be equal to 1 and y cannot be equal to 3. So now when I'm looking at my points, here I'm thinking about this -2 here. So I'm going to be thinking of pairs of numbers that multiply out to 2, and I'm going to be putting them over here. So starting from this spot here, I'm going to be thinking about two numbers that multiply out to 2. And you can see how this one works. If I go left 1 and up 2, 1 times 2 is 2. I can go left 2, up 1. I can go left 1, 2, 3, 4, up a half, and so on. So I think I'll just draw this in now. Now looking over here, again, I need to find two numbers that multiply out to 2, so I can go over 2, down 1, 1 over, down 2, 1, 2, 3, 4 and a half, or I can go a half and then 1, 2, 3, 4 over here. So now if I draw it out, and you'll see it does hit that spot just about where we planned it, and we have a few points here. Okay. Explain the behavior of the graph near the non-permissible value. So that's the first part we're going to do now. And the second one is the end behavior. So the non-permissible value, in this case, the NPV, is equal to, well, it's like what can x not be? X cannot be equal to 1. So what's the behavior of that? Well, as x gets closer and closer to 1, my y values gets closer and closer to either positive infinity or negative infinity. So my first part for that is as x approaches 1, my y value approaches positive and negative infinity. Okay, my second one is the end behavior, so on the right hand side and the left hand side. So as x gets closer to positive infinity, my y value gets closer and closer to 3. As x gets closer to negative infinity, my y value again gets closer to 3. So I'm going to say as x approaches positive or negative infinity, y gets closer to but never touches, it approaches 3. Okay, so in this case when I'm doing those arrows, my arrow really stands for approaches. Gets close to, but never actually touches, and that's what an asymptote is. Alright, now before we go on to example number 3, I think this would be a good place to pause. So I'm going to stop, I'll record this video, and I'll upload the next one for you starting example 3.